Imagine trying to drive a car where every steering input takes over a second to happen. On the moon, that 1.3-second light speed delay isn't just a laggy connection, it's a mission killer. When you're navigating a multi-million-dollar rover through uncharted craters, waiting for Earth to tell you to stop is a recipe for disaster. This is the physics wall we've hit for decades. But a new partnership between HPE and Astrolab is about to change the rules of the game. They aren't just sending a rover, they're sending a supercomputer with its own brain.
Meet the FLIP rover. It's Astrolab's answer to lunar logistics, designed to carry heavy payloads across the most brutal terrain imaginable. But its secret weapon isn't its wheels. Tucked inside its chassis is the HPE spaceborne computer. This is the same architecture that's been battle-tested on the International Space Station, now shrunk down for a lunar marathon. By moving the processing power to the moon itself, we're effectively moving the mission control room into the rover's driver's seat. This is the birth of true lunar edge computing.
Standard space missions rely on bent pipe communication. You send raw data to Earth, wait for a human to look at it, and wait for a command to come back. But the HPE spaceborne computer changes that. It processes data locally, allowing the rover to make decisions in milliseconds rather than seconds. It's the difference between a reflex and a conversation. This isn't just about speed, it's about survival. In the time it takes for a signal to reach Earth, a rover could have already rolled into a permanent shadow or a hidden crevasse.
To make this work, the hardware has to be incredibly efficient. We're talking about running high-level AI models on a power budget that would make a gaming PC laugh. HPE uses advanced software-based hardening. Instead of just heavy lead shielding, they use clever algorithms to detect and fix errors caused by cosmic radiation in real time. This allows them to use modern, off-the-shelf components that are orders of magnitude faster than the ancient radiation-hardened chips used in the 90s. It's a massive leap forward.
The result? A rover that can see, think, and act on its own. It's the first step toward a fully autonomous lunar economy, where machines do the heavy lifting without human hand-holding. But navigating the terrain is only half the battle. The real prize lies hidden beneath the regolith, and to find it, the AI needs to become a geologist. Next, we're diving into how this AI actually sees the resources that will power the next century of human exploration. And trust me, it's smarter than you think.
The moon isn't just a rock, it's a gas station for the solar system. The two biggest prizes, water ice for life support and helium-3 for clean fusion energy. Finding these resources is incredibly difficult. Helium-3 is trapped in the top layer of dust, and water ice hides in permanently shadowed regions where the sun hasn't shone for billions of years. Traditionally, we'd have to take a sample, analyze it, and send the data home. But the FLIP rover does the chemistry in its head, using real-time AI computer vision. Using the HPE spaceborne computer, the rover runs deep learning models that can identify the spectral signatures of ice and minerals instantly. It's like having a team of scientists on board. This onboard AI doesn't just look at pictures. It processes multispectral data, looking for the specific way light reflects off different molecules to find the good stuff. By the time a human on Earth would have even seen the first frame of video, the rover has already mapped the deposit and calculated its volume. That's the power of the edge.
Why not just send the data to Earth? Because bandwidth is expensive and limited. Sending raw high-resolution sensor data would clog the radio waves for hours. Instead, the AI acts as a filter. It processes the gigabytes of raw data locally and only sends back the answers, the coordinates, and the composition. It's incredibly efficient. This allows the mission to move faster. We can cover more ground in a single lunar day than we used to cover in a year. We're talking about a 100x increase in exploration speed.
But wait, there's a catch. AI isn't perfect. Even the most advanced models can experience hallucinations, where they see patterns that aren't actually there. In a lab, a hallucination is a funny error. On the moon, if the AI thinks a shadow is a solid path, the rover could drive right off a cliff. The stakes are literally astronomical. To solve this, HPE and Astrolab use ensemble models, multiple AI systems checking each other's work. It's a digital democracy where the majority must agree before the rover moves.
This autonomous detection is what makes a permanent lunar base possible. We can't ship everything from Earth. We have to live off the land. And the FLIP rover is the ultimate scout. But even the smartest AI is useless if the hardware freezes or melts. The lunar South Pole is one of the most hostile environments in the solar system. How do you keep a supercomputer running when the temperature swings by 300 degrees? That's the engineering nightmare we're tackling next.
The lunar South Pole is a land of extremes. You have peaks of eternal light and craters of eternal darkness, where temperatures can drop to -400 degrees Fahrenheit. For electronics, this is a death trap. Traditional batteries fail, and silicon chips become brittle. Keeping the HPE's spaceborne computer alive requires some of the most advanced thermal management ever built. Astrolab uses a combination of passive insulation and active heating, fueled by the rover's solar arrays, to maintain a Goldilocks zone for the AI's brain. Then there's the radiation. Without an atmosphere or a magnetic field, the moon is pelted by high-energy particles that can flip bits in a computer's memory. HPE's solution is redundant processing. The computer runs the same calculation multiple times and compares the results. If one result is different, it knows a radiation hit occurred and discards the error. It's a software-first approach that allows the rover to use powerful, modern chips instead of being stuck with slow, hardened hardware from the Apollo era.
The biggest challenge for the AI, though, is the shadows. At the South Pole, the sun is always low on the horizon, creating long, deceptive shadows that can hide giant boulders or deep pits. This is where hallucination risks are highest. The AI might try to fill in the blanks of what's in the dark, potentially imagining a flat surface where there's actually a crater. To counter this, the Flip rover uses LiDAR, laser pulses that can see in total darkness. By combining AI vision with LiDAR, the rover creates a high-fidelity 3D map that doesn't rely on sunlight. This integration of HPE's compute power and Astrolab's rugged mobility is a blueprint for the future. We're not just visiting the moon, we're setting up a permanent presence. The lessons we learn here about edge computing, autonomous resource detection, and hardware durability will be the foundation for missions to Mars and beyond. Because when the nearest help is millions of miles away, you'd better have a computer that's smart enough to handle the journey on its own.
The HPE spaceborne computer on the Flip rover isn't just a tech demo. It's the moment space exploration stopped being a remote-controlled hobby and started being an intelligent industry. We are finally breaking the speed of light barrier, not by moving faster than light, but by being smart enough not to need the signal in the first place. The moon is waiting, and for the first time, we're sending a mind that's ready to meet it. The future of the edge is looking very bright and very lunar.